Welcome. I want to talk again about the geodesic flow, which is defined in a manifold, discrete manifold of arbitrary dimension. What we just want to have is that it's a q-dimensional pure simplicity complex, such that every q-1 dimensional wall, like here in these 3 dimensions, every triangle has exactly 2 maximal simplices attached, and then we can define a dynamical system on the frame bundle of this geometry. It's a perfectly defined permutation. We have a choice kind of here to rotate left or rotate right, and I want to make use of this in order to get to an interaction. We want to have not only one particle which moves on a geodesic, but we want to have several particles, maybe 100,000 particles moving on geodesics, and they are allowed to interact on a simplex. They come together, maybe they have different orientations, but they come together, and then we want to decide what happens with this. I implemented that here with a choice which I want to kind of justify. So I believe there is maybe only one possible choice which makes sense, especially if you want to go into division algebras. So what I like about these division algebras is that you have this inevitability. You have this kind of finitely many structures which are forced by, for example, assume associativity and finite dimensional division algebra. So, or you kind of ask for norm real, right? So that there are also octonions, but associativity is not there. Complete associative, complete is very nice. You want to have completeness, which needs to be defined properly in the case of quaternions, but in complete associative division algebras are just C and H. And in 2016, it's almost 10 years ago, I was working on quaternion primes and Gaussian primes, looked at Goldbach and all kind of interesting problems one can look at. And I also saw that there is kind of a nice equivalence class structure, which reminds of particles you see in nature. Like if you look at the primes in the quaternions, so there are 2 types of primes. There are the Lipschitz primes or the Hurwitz primes. Some of them have integer coordinates, some of them have half integer coordinates. So this is a Lipschitz prime, this is a Hurwitz prime. They are equivalent, right, because they belong to the same, they have the same norm. The norm, so over every prime p, rational prime p, there are just p+1 primes in the quaternions, and you can Hurwitz analyze that more than 100 years ago, and one can look now at the primes, and then you just put them into the first quadrant or hyperquadrant, and then you look at equivalence classes modulo the units, which is gauge transformations, right? The units are gauge transformations, and then you get actually either 1, which is the prime 2, like 1, 1, 0, 0, and you get the meson structure like here, or you get the baryon structure like here. So you see hadrons in these primes. So that's intriguing. And you see lepton structures in the complex. So you have them kind of associate with real primes, which are of the form 4k+3. You associate neutrini, these are fermions, and then there's also fermions. And then you look at the electrons, which are they decay, right? So the primes of the form 4k+1, that's the Christmas theorem of Fermat, they decay into 2 fermions. So these primes actually, kind of these rational primes, are not primes anymore in the complex. You can decay, yeah, they decay. And so you have kind of this, you know, affinity with particles in the standard model. So you can, primes 2 here play a special role. Maybe that's the Higgs. I don't know. This is kind of something you can play with. Anyway, this is just an affinity, an association. It's nothing more. But we would like to play with that, and if we play, we want to have a toy, and if we want to have a toy, we want to have a good toy. We want to have fun with it. And so what is nice is now to think about, you have two particles coming together. How do you, or two geodesics, which kind of particles moving on geodesics, they come together. How do you make them continue, and what is a natural interaction? So the velocity is played by the permutation which you have on the simplex. So the simplex has, in this case, they are just 4 factorial of 24 different orientations, and so each orientation is like a velocity. And so if they come together, what you want to do, maybe you have 1,000 particles, they come together, and then you look at the simplex, how many particles are here. This, in the case of quaternion valued divisors, right? If you think about it as divisors, because you just want to know how many particles are there at some point. This is just integers. And then if you have different flavors, so you have these quaternion integers, or complex integers, Gaussian integers. And then what is nice is there is essentially just one completely multiplicative function which you can define in these algebras, and that's the on integers, which is the Liouville function, which just takes -1 to the number of primes. There is not a unique prime factorization here, but essentially unique modulo some unit migration. You can put the units anywhere. Of course, that because of non-commutativity, you can put them, you know, when you put them at a different place, it becomes another unit. Recombination and metacommutation. So you can put 2 primes which multiplied give a rational number. You can put them anywhere because then it becomes commutative. But essentially, this is the only thing. So the number of primes which you have, a number in the quaternion integer decays into a number of primes, and this number is uniquely defined. And then you can define -1 to that, which is close to the Möbius function, but you don't take, the Möbius function would give you 0 if you 2 primes appear twice. So this is, the Möbius function is not completely multiplicative. This is completely multiplicative. It's better than that. And so, and that's what I kind of started to implement. On a cellular automata level, of course, that's simpler to experiment with, especially if you have many particles and a large space, and I have implemented that here just with usual integers first. So I'm not even looking at Gaussian integer valued divisors, or quaternion valued divisors, but just integer valued divisors, which are just particles of essentially what you have is just you have these 2 particles, which then when they come together, you decide what happens with this number. You decay it into primes. You can see how many primes are there, and then depending on that, you choose either the t plus or the t minus. So that changes, right? So that they interact now at the point. We have locality, we have determinism, we have no problems with commutativity, right? Even in a non-commutative situation, like the quaternions, or if different particles come, what happens is, even in the classical collision of 3 billiard balls, it matters which comes first and which comes after. So it's not defined. The interaction of 3 particles coming together at the same point is not defined in the classical setup. But here everything is completely deterministic, everything works. Whether it produces something physically relevant, I'm actually not so worried about now. I mean, this is just a nice toy model. And what I'm worried about is that I don't want choice. I want to have a unique interaction which is natural and hopefully gives some interesting, interesting models. And the next thing I want to do is to implement that, first of all, for Gaussian integers, which just means you double the number of matrices, which I need here, or quaternions, where I have 4 times as many matrices. But the code which I have here is essentially, a dozen lines or 15 lines, and it doesn't get much more complicated like that. That's it for today.